Hi, I am Zorol. I would like to introduce our paper, Random Walk on Pixel Manifolds for Anomaly Segmentation of Complex Driving Scenes. Anomaly segmentation is an important task for autonomous driving systems. It helps the system detect anomalous objects on the road. Now, most anomaly segmentation methods design and use anomaly scoring functions to calculate anomaly scores for each pixel based on the logits output by the segmentation model. Thus, accurate logic prediction is crucial for inferring anomaly score. In real-world scenarios, environmental factors like weather and illumination create diverse driving scenes, which often affect segmentation model outputs due to training data limitations. However, current methods often overlook this issue. From the embedding space perspective, driving scene diversity distorts manifolds in the embedding space. Since logits predictions rely on the cosine distance between pixel embeddings and classifier weights, this distortion affects the accuracy of the predicted logits. However, previous studies show that despite distortions, similar data still remains within the same manifold, indicating that the manifold structure contains intrinsic relationships of data. Inspired by this, we aim to propose a method to reveal the intrinsic relationships between pixels through the structure of pixel manifolds, thereby optimizing the distribution of pixel embeddings and mitigating the effects of data diversity. In this paper, we propose a post-processing zero-shot method called Random Walk on Pixel Manifolds, RWPM. It can be applied during inference without additional data, training, or network modifications. Next, I will introduce the proposed RWPM, which consists of three parts: graph construction, random walk process, and partial random walk. The first part is graph construction. For each input test image, the backbone of the segmentation model is first used to extract pixel embeddings, P. For convenience, we reshape P and normalize each row to obtain hat PR. Then, by calculating the inner product, we obtain the affinity matrix W. Finally, by normalizing W, we get the corresponding graph S, which describes the manifold structure. The second part is the random walk process on the pixel manifolds. We first initialize M0 as PR and then iterate on the graph S. In each iteration, each pixel diffuses its information to other pixels while receiving information from other pixels and updating itself accordingly. The final result can be obtained in closed form, and the resulting M-INFD becomes the refined pixel embeddings for the subsequent anomaly segmentation process. The final part is partial random walk. Large input images lead to large matrices for random walk calculations, increasing computational and memory costs. For instance, a 5112 by 1024 image results in a huge graph matrix, significantly slowing running speed. To address this issue, we propose partial random walk, which consists of two parts. The first part is limited iteration. We perform only T iterations instead of using closed form. We found that a few iterations can reach good results while significantly reducing computation. The second part is embedding map partitioning. We equally divide the pixel embedding map into several submaps and then perform random walks on each submap. Finally, we concatenate the results from each part. This strategy can also significantly reduce computational costs. Additionally, to minimize errors caused by differences between the submaps, we can use calibration to smooth the results of each submap during concatenation. Finally, we conducted extensive experiments to verify the effectiveness of RWPM. First, we applied RWPM to 4 representative anomaly segmentation methods in different network architectures. The results show that RWPM can significantly improve the performance of these methods. Next, we applied RWPM to one of the anomaly segmentation methods, RBA. We then compared the results with other state-of-the-art anomaly segmentation methods. The results show that RWPM consistently achieves high performance across various datasets. Finally, we present some qualitative results. We can see that RWPM significantly improves the results of RBA, reducing both the false positive rate and false negative rate. Thank you very much for your attention. You can access the code and more information about the paper through this QR code.